Hello and welcome to this Mr. Cole chemistry video where I will be going through the answers to the kinetics practice test. During that time I will be going through the answers, but I will also be looking at some of the context and some of the background information that you need to know in order to be able to access the questions. Okay, so question 1 is a definition question, and you do have to know this. Now most people will have a kind of vague concept of what rate of reaction is, the idea of a reaction being faster or being slower, but it's really important that you actually understand what the actual definition is. In order to be able to do this, you need to think about the units. So the units for rate of reaction are normally measured in moles per dm cubed per second, okay, which means that it's looking at concentration as the unit for our substance. Okay, yes, you can measure all kinds of things. You can measure the mass produced, you can measure the volume produced, you can measure the number of moles in all kinds of ways, but the official one is concentration. So the definition is the change in concentration of you can have a reactant or product here, doesn't matter. So change in concentrate, I've shortened concentration to conc, change in concentration of a reactant or product in a unit time, per time. You can just say per unit time, or you can give a specific answer like per second, which would make sense given the units. So change in concentration of a reactant per second would be a good answer. Okay, so the next one is to state and explain what has happened to the rate of reaction at point W. So looking at W here, you have to be able to tell that the gradient has reached 0 at W, so the gradient has flatlined, isn't it? Okay, and you've got to be able to tell what the gradient is. Well, if the gradient is change in Y over change in X, it's volume of hydrogen per time. Now, I did just say we don't measure it in volume per time, but in this example, that's the only way of measuring it, which means that the gradient is your rate of reaction. So if your gradient has flatlined, your rate of reaction has reached 0. So rate has reached 0. And of course, the reason for this happening is, over time, you can see that the rate gets slower and slower and slower because the rate of reaction is getting slower and slower and slower because the concentration of your reactants is gradually going down. Most likely, the concentration of hydrochloric acid is going down. The point where the concentration reaches 0, or you've run out of reactant, is the point where the reaction stops. So, run out of reactant. Now, you've got to be careful because when I said run out of reactant, do we know which one is an excess? Because if we know which one's an excess, then it's the other one. So we look at the question. It says, show the volume, figure 1 shows the volume of hydrogen gas when a sample of magnesium is reacted with excess dilute hydrochloric acid. Okay, so when it says run out of reactant, actually, we have to be specific. It's magnesium. Okay, moving on to question part 3. So in terms of collisions theory, explain why at a fixed temperature the rate of reaction doubles when the concentration of the hydrochloric acid doubles. Okay, so this is only a 2-mark question, so we don't need to go into super loads of detail, but we do need to be able to use kind of concepts of collision theory. So whenever we're looking at collision theory, we are thinking about the frequency of successful collisions and what is happening that causes the frequency of successful collisions to increase. Whenever you're considering the frequency of successful collisions, so frequency of successful collisions, there's 2 possible reasons. You got frequency of collisions or proportion of successful collisions, or proportion of collisions that are successful. Okay, in this case, we're not affecting the proportion of collisions that are successful. That's all just to do with energy. Energy is not changing. So it's the frequency of collisions that's important here. So why does the frequency of collisions increase? Well, it increases because there are twice as many hydrogen ions present in solution. So double the number of H plus ions in solution. I've said in solution, to be honest with you. Have we been given the volume? We haven't been told the volume. So double the number of in the same volume. And therefore increased frequency of successful collisions. Now, note, I've said double the number of hydrogen ions, not number of HCl's or anything like that. Of course, we know in this reaction that HCl is a strong acid. We know that it is the H plus ions that are going to be reacting with the magnesium, and therefore it's that concentration that matters. Now, the mark scheme says you can say twice as much hydrochloric acid or twice as many particles, but to be honest with you, I think those are relatively generous answers on the mark scheme. You really do want to be looking at specifically what's happening. In some cases, you won't be able to tell what's specifically happening, but in this case, you know what happens. You know that it's hydrogen ions that react with the magnesium, so those are that's the concentration you need to be talking about. Okay, moving on to question B. So question B is another definition. It is just a 1 mark definition. So the activation energy is the minimum energy for a reaction to start or to go. I don't really like that. The second definition that they give there is the minimum energy for a successful collision. That's my preferred answer. So minimum energy for a successful collision. Okay, moving on to question part 2. So complete figure 2 by drawing the shape of the reaction profile from reactants to products, form an exothermic reaction, show the position of the products, show and label the activation energy. Okay, so the products we know is going to be lower than the reactants. Make sure you have labeled it as products. And then make sure your activation energy goes up, and then it falls. It does say to label your activation energy. So, labeled activation energy. Okay, so your first mark is making sure your products is lower than the reactants and having make sure you've actually labeled your products. And then the second mark is for having the activation energy and actually labeling it, having that arrow there with EA or activation energy. Do please leave a direction on your arrow, okay? The same way as if they had asked for you to write in the enthalpy change, there would be a direction on that arrow because you do have the concept of a forward reaction and a backwards reaction in this particular case, okay? So yeah, make sure there's no double arrowhead on your activation energy. Okay, moving on to question C. So question C is the reaction of barium with water. Okay, we've got some group 2 inorganic chemistry sneaking in here. So barium with water, you have to know that, of course, barium is an alkali earth metal. It will react to form a hydroxide and hydrogen. So make barium hydroxide and hydrogen. I've not put state symbols in. It's not clear whether we have to, so I'm going to go back and I'm going to put them in. The easy ones in first, leaving us with the barium hydroxide. Okay, barium hydroxide. Is it soluble? As you go down the group 2 hydroxides get more soluble. So barium hydroxide is soluble. Question part 2. A solution containing barium ions can be used to show the presence of sulfate ions in an aqueous solution of sodium sulfate. Write the simplest ionic equation for the reaction that occurs and state what is observed. So it's the reaction between barium ions and sulfate ions. So barium ions and sulfate ions going to form barium sulfate, and always put your state symbols in for these sorts of ones. The mark scheme does say to ignore state symbols, but put them in. It's never wrong. State what is observed. So barium sulfate is a white precipitate. Okay, and moving on to the very last bit of question 1. So state one use of barium sulfate in medicine. Explain why this use is possible, given that solutions containing barium ions are poisonous. So again, a bit more group 2. If you've not done group 2, then you're not going to be able to access this question. So you'll probably just have skipped that out. Barium sulfate, barium ions are toxic. Okay, or poisonous, as I've said in the question. However, it's really it's important to note that things are only toxic if they can get into you. And when I say into you, I mean into your cells or through your cells. So if you were to swallow some barium and it was to be in your stomach or your intestines, that doesn't mean it's actually inside of you. Like it's not actually in you yet. Your digestive system, bizarrely, is outside of you. You're sort of a hollow tube, when you think about it. And it's only when the barium moves from your digestive system, so from your intestines, into your bloodstream, would it become poisonous. So the question is, what things can be absorbed? Well, things that are soluble are absorbed. Things that are insoluble are not absorbed. Okay? Rule of thumb. Not 100% true, but good enough. So barium that is soluble will kill you. Barium nitrate will kill you. Barium sulfate, however, will not kill you. So you can swallow barium sulfate, and it will just pass straight through you. So the question is, why would we want to swallow barium sulfate? Well, barium sulfate is opaque to X-rays, like bones are, which means that if you consume a load of barium sulfate as barium swallow or barium meal, okay, so question 2, we've got ourselves a Maxwell-Boltzmann distribution, and 2a is to label the y-axis on the figure above. So that is number of molecules. Number of molecules. The mark scheme says to ignore particles or atoms. You definitely want to ignore atoms, because the number of atoms, of course, is different depending on what your molecule is. Strictly speaking, these are molecules because Maxwell-Boltzmann distributions are for gases. In fact, it tells you that in the question. Energy is in a sample of gas. Your gas is going to be a molecule. Okay. I challenge you to find a gas that isn't a molecule aside from the noble gases. Okay, so and also tells you in the question molecular energies. So there you go, there's a clue. That's why you can't say atoms. Okay, question 2. State why the curve starts at the origin. It's because there are no particles with no energy. It's a slightly odd fact that no particles with no energy, that you can't actually find particles without any energy. You can't actually find particles at 0 Kelvin. We've got extremely close in some labs, but we've never managed to get something at 0 Kelvin. So you can quite happily start your line at the origin. Okay, then we've got a question of what X is on the figure above. Okay, so it's not the mean energy. Lots of people think that it's the mean energy. That, of course, is the most probable energy. Okay, so most probable energy. Make sure you get the right axis. So of course it's the most probable energy. It's not the number of molecules with the most probable energy, which of course would be if the line was going across to your y-axis. Moving on to question D. Half of the gas molecules in the sample are removed. The remaining molecules are kept at the same temperature. Draw a new distribution of molecular energies for the remaining gas on the figure above. Okay, so you're told that the amount of energy is not changed, or the distribution of energy is not changed. So the amount of energy has actually changed. It's halved, but you got half the number of particles. So the average energy kind of stays the same. Distribution of energy has remained constant. You have half the number of particles. So what we're looking for is a most probable energy that's at the same energy, but we're looking to have fewer molecules. So we're looking, let's try and get it so it's more like half. No, not doing a very good job here. There we go, that's more like it. Okay. Ooh, is that okay at the end there? Not sure it is. We need to make sure that those lines don't meet. I promise you this is slightly easier on paper than it is on a tablet. Okay. There we go. That's a bit more like it. Maybe my peak's a little bit low. Should we go for third time lucky? Let's go for third time lucky. Okay, so it should look more like that. So the mark scheme says peaks should be the same energy. Peaks at the same energy. And the overall energy should be half the area after diverging from the origin. The second line should not touch the first. Okay, so we shouldn't have any touching going on here. Is my area half that on the thing? I think it's close enough. Okay, which moves us on to question 3, which is a multiple choice question. So which statement is correct for the distribution curve of molecular energies of a gas? So statement A, the curve is symmetrical about the maximum. No, we know that's not true. We know it's asymptotic. We have that shape earlier there. You can see it's not symmetrical, so it's definitely not A. Statement B, there are always some molecules with zero energy. No, that's not true. We've already talked about that. No particles have zero energy. The position of the maximum of the curve is not dependent on the temperature. The position of the maximum on the curve is not dependent on the temperature. No, that's definitely not true. When you increase the temperature, the maximum shifts towards the right. If you decrease the temperature, the maximum shifts towards the left. So no, that statement's not true. Must be D. Let's check it. The mean energy of the molecules is greater than the most probable energy of the molecules. Yes, this is absolutely true. So if we look up here, our most probable energy is our kind of our peak there. The mean energy is going to be sort of like that point there-ish. So yes, statement D is correct. Moving over to question 4. Okay, so on the same axis, draw a curve for sample 1 at a lower temperature, 2 marks. Okay, so you're starting at 0 as always, and you want your curve to be kind of squashed in towards the left. However, you can't have a lower area. Your area needs to stay the same. Okay, so you want something that looks a bit like this. So, marking 1, the curve is higher and displaced to the left. Yep, we got that. Marking point 2 only crosses the original curve once. So I got my crossing here. Doesn't cross it back over here. Okay, lots of people for some reason draw it coming back again. Doesn't do that. Only crosses it once. Question B, explain the effect that lowering temperature will have on the rate of reaction. So this is just a standard collision theory explanation. In fact, it's very straightforward because you have to state the effect, which will give you a 1 mark, which is that it will decreases. And then you have to explain why. And actually looking at the mark scheme, you don't get a mark for saying it decreases. That's a piece of information you're expected to say just for free. So rate decreases, and fewer particles will have energy greater than the greater or equal to the activation energy, and therefore there will be fewer successful collisions or less frequent successful collisions. So we're always considering that frequency of successful collisions. So frequency of successful collisions decreases. And of course, this is because the number of particles, they've used the word particles in the mark scheme. I probably wouldn't. Looking at it, can we tell what's actually happening in terms of the mechanism? No, we can't. We'll stick with particles. Number of particles with at least the activation energy has decreased. Okay, moving on to question C. So deduce the change that was made to the reaction conditions. Explain the effect that this has on the rate of reaction. Okay, so our most probable energy hasn't changed. So the temperature is not affected, but the number of molecules has been decreased because the area underneath sample 2 is lower than the area underneath sample 1. Okay, so number of molecules has decreased. They have in the mark scheme said the pressure has been reduced, which is not really true. If the pressure had been reduced by removing molecules, then yes, but if the pressure had been reduced by increasing the volume of the container, then no. So it's not a good answer. Don't give that answer. Frame it in terms of what's on the axes. Number of molecules. Okay, so number of molecules has decreased. You then would have to say that the rate decreases, which doesn't get you a mark. You have to do it through the explanations. And again, we're talking about the impact on the frequency of collisions, which of course is because the particles are further apart, and therefore decreased frequency of successful collisions. So again, you're always bringing it back to the idea of frequency of collisions, what's happening to it, and what's causing that to happen. Okay, so question 5 is looking at the line of X, which was made by reacting magnesium with 30 centimeters cubed of 1 mole per dm cubed hydrochloric acid. The reaction was repeated using 20 centimeters cubed of 2 mole per dm cubed hydrochloric acid. So the concentration has doubled, but then it has used only 2/3 of the volume. So I'd always start by working out the number of moles that's going to be produced in each of these cases. You can do these generally just by kind of like eyeballing it, but actually in this case it's really quite straightforward just to calculate the number of moles in each case. So for the original line X, the number of moles is, it's actually not going to be moles, I'm just going to use centimeters cubed rather than dm cubed, it doesn't really matter. So it's just 30 times 1, which gives us 30. Note that it is on line 3, so each line must be 10. Then the moles for the kind of the new reaction is 20 centimeters cubed at 2 moles, so 20 times 2 gives us 40. So it was 30 moles of hydrochloric acid, of product originally, and now it's 40 moles. So where it was previously 3, line 3 is now going to be on line 4, which means it must be B. Okay, moving on to question 6. So explain how a catalyst increases the rate of reaction. This is actually the one case where you don't have to talk about the frequency of successful collisions, because that bit sort of comes later in the explanation. You just have to talk about the effect it has on the activation energy and, of course, why it does that. So alternative mechanism, alternative reaction mechanism. Often, previously at GCSE, you might have had it described as a pathway, but we talk about mechanisms all the time at A level, so we'll use that terminology here as well. And of course, that lowers the activation energy. Okay, moving on to question B. So we got the Maxwell-Boltzmann distribution given there. They've shown us where activation energy is. They've shown us where the most probable energy is. To answer questions C1 to C4, you should use the words increase, decrease, or stays the same. You may use each of these answers once, more than once, etc. Okay, so state, if at all, the values of the most probable energy changes as the number of molecules is increased at a constant temperature. So the temperature is kept constant, but the number of molecules is increased. So if we were to draw a graph for that, we would expect to see a larger area under the graph, but the energy distribution would be exactly the same, so it would just be a taller graph that looks like that. Most probable energy will stay the same. Question part 2. So state how, if at all, the numbers of molecules with the most probable energy changes as the temperature is decreased without changing the total number of molecules. So again, let's just sketch out a graph. We've decreased the temperature, so we're seeing a graph that looks like that. So the question was, what happens to the number of molecules with the most probable energy? Well, if we look at our graph there, I've gone off the edge of my graph, there we go, it is higher. So increased. Question part 3, state how the number of molecules with the energy greater than the activation energy changes as temperature is increased without changing the total number of molecules. So we've increased the temperature this time. So let's have a look to see what that graph looks like. And as you can see, we've increased the temperature, we've increased the number of particles that at least have the activation energy. And the last one, what happens if we add a catalyst? Well, if you add a catalyst, the only change that you introduce is by having a new activation energy, and of course the line of distribution has not changed. So no change. Question C is identifying catalysts and the products. So fermentation of aqueous solution of glucose. So this is fermentation to form ethanol. So our product is ethanol. And the catalyst that's required. The mark scheme says you can say the word yeast. I'm not a big fan of saying that because that's not a catalyst. The catalyst is the enzyme that the yeast produces, which is zymase. So zymase, which produces ethanol. Question C2 is for the hydration of butene. So hydration is, of course, adding water to something. If you've got a double bond and you are adding water to it, you are going to add a hydrogen to one and OH to the other, which means, of course, we're going to end up making an alcohol, and it's going to be on the second carbon, which, of course, is going to then be making butanol. The mechanism for this involves a strong acid catalyst, which is either phosphoric acid or sulfuric acid. I'd just like to take this opportunity to remind you of the mechanism of when an alkene is attacked by a acid catalyst. So just make those R groups for now. Okay, so a double bond attacks the hydrogen ion from the acid, which could be from the phosphoric acid or could be from the sulfuric acid, and that's of course going to result in the addition of the hydrogen there, and then that becomes the carbocation, and then the carbocation is attacked by the water, which results in our second intermediate, which is this version like this. And then of course one of these hydrogen atoms, the bond breaks, and that forms our alcohol. That of course is the simplified version, which is just using the H+ ion to represent the catalyst. You can of course use sulfuric acid in this process, and draw out the kind of the full molecule there, and then have one of the hydrogens. This hydrogen here is actually being attacked by the hydrogen sulfate. Okay, looking at question 7, labeling the axis, the horizontal axis this time. So that is energy. Yes, you can call it kinetic energy if you want, but energy is fine. On the graph, sketch a distribution of molecular energies for the sample gas at a higher temperature. So remember, it starts at the same point, but then looks more like that. Okay, so just remember that most probable energy is shifted right and is lower, and then they never meet again in the middle. The two lines never meet again. Okay, then looking at question C. Now, question C is actually a bit strange because it's a decomposition reaction, and I would question the validity of talking about collisions in a decomposition reaction. That said, the mark scheme doesn't acknowledge this at all, and therefore we will just be talking about collisions. So, increase in temperature. You've got two choices when it comes to increasing temperature. You can talk about the increased energy of the particles, or you could talk about the frequency of the collisions because of the speed. I would always go with the increased energy of the particles because that's a much greater effect. So more particles or more molecules have at least as much energy as the activation energy, and therefore increased frequency of collisions. Successful collisions. Okay, that brings us to the end of this walkthrough of the kinetics test. If you have any questions about any of this, or if you have a question, one of the questions that you think wasn't answered fully, then please leave a comment down below. If you like the video, then please find your finger moving in the direction of having a successful collision with the like and subscribe buttons. I apologise, that was a terrible joke.